Okay, so this is the page 3 stuff. Kind of gets into territory that's maybe less familiar because it's been a longer time since we've dealt with some of this. But we're talking about points and polar points. Remember, they're slightly different. Polar points are, there is an R, a radius that you walk out. You face an angle of a certain amount, negative 210 degrees, and then you walk out a radius of 4. So when you plot these points, so part A, you're going to face the 210, and you're going to walk, or negative 210, sorry about that, and now negative means you go counterclockwise. Here's negative 180, but then to go to 210, you go 30 more. So there's negative 210, and then you walk out 4 units, 1, 2, 3, 4, to land on that point A. And facing 135, and then walking out negative 2, if you face 135, which is up here, 135 degrees, walking negative 2 is to face that angle and then walk backward. And that's just the idea of polar points. Now, polar points are points, and you certainly can plot a polar point by using XY coordinate points, going left a certain amount and up a certain amount for the part A point, and going to the right and down a certain amount to get to point B. But they're just different ways of describing arriving at a singular point. Now, the next part, convert this polar point to the Cartesian or rectangular. And if you have an R and a theta, which is what polar points are organized by, there's a quick way to get your x. Your x is from r cosine of theta, and so here's r, 3, and cosine of theta to get my x, and then the y component is going to come from y equals 3 sine of theta. And then down below, just with the unit circle in mind, remember this will be a no calculator section, cosine of pi over 3, what's the x coordinate on the unit circle at angle pi over 3, and that's half. And 3 sine pi over 3 is the y coordinate at pi over 3 on the unit circle, and that's square root of 3 over 2. And if you multiply those by 3 respectively, this is the exact point, no decimal included, using the unit circle to evaluate that. Okay, next page, next problem is convert the rectangular to polar coordinates. So these are xy coordinates, negative 6 and negative 8 respectively. And there's a quick conversion because the way polar works, this is the relationship that we've been using all along. It's that a polar point and a rectangular point are related by the xy coordinate points that we're used to can also be described by a theta and a radius. And they both are ways of saying, hey, where's that point located? So to convert between those, it's just any formula you know relating x, y, and r in this right triangle. So the things that we know about are, the Pythagorean theorem, x squared plus y squared is r squared. And we also know that there's a trig function, tangent of theta is y over x. And those are both things that we can manipulate a little bit. And if we do, we could come up with even more direct equations like, well, x squared plus y squared is r squared. Wouldn't that mean that r is just the square root of x squared plus y squared? Sure. So that's what I'm using over here. And that would be 6 squared plus 8 squared gives you 100. Square root of 100 is 10. And then, hey, if tangent of theta is y over x, doesn't that mean the inverse tangent of y over x is theta? Sure does. So here's the inverse tangent of y over x, and you get 53 degrees. And in this particular case, if you plot the point negative 6, negative 8 on a coordinate plane, that's left 6, down 8, that is a point in the third quadrant, and 53 degrees is an angle in the first quadrant, so you'd have to add 180 to make this an accurate angle, and here it is. So the radius of 10 from square root of x squared plus y squared, and the theta of 233.1, which is inverse tangent of y over x, and then we had to add 180 because of the particular point we were graphing. In part D, we're converting equations. So you can actually, remember, we use Desmos to graph this equation, r squared equals r sine of theta. It's an equation that graphs something familiar, and actually if you go look at it, we can see kind of a shape that is graphable in the xy coordinate system. The way you convert them is there's certain things you want to exchange. We know certain equations, you need to be aware of certain equations, like x squared plus y squared is r squared, and that is important. That's if you ever see an r squared like we see on the left-hand side of this equation, you can replace it with x squared plus y squared. So that's the first step you're probably noticing here in this particular equation. There's our replacement. And then the others are, there's a few of them, but x equals r cosine of theta, and y is r sine of theta. So should you ever see a y lying around, you can replace it with r sine of theta, or vice versa. If you see r sine of theta, replace it with a y, and that's the case where we have an r problem. So if you go over here, r sine of theta has been replaced with y. This is essentially done. I mean, this is a perfectly good rectangular equation, and you could, somebody might ask you to solve for y, but that would be kind of a cruel and unusual punishment. Right now we're just, you understand, converting means if you have an equation with r's and thetas, it needs to be replaced such that you have x's and y's when you're done. And then vice versa, if you have an x and y equation, a Cartesian type equation, you need to find a way to replace all those x's and y's with r's and thetas. It's really quick. X is r cosine of theta, boom. Y is r sine of theta, and so you see that y is going to be replaced with r sine of theta. This is done once we replace x and y, and it's replaced with some form of r and theta. You're actually technically done. But most of the time there can be a need for you to maybe get r by itself and graph, because our graphing calculators, for instance, in polar mode ask you to get r equals equations, so you'd have to get r by itself. If that were the case, you'd have to factor out an r and have, cosine of theta minus 3 sine of theta, and maybe do some algebra. This particular problem is not conducive to that, and it's probably more complicated than necessary. So this isolating r, let's just bypass that for right now. For a few tables, actually during this review, I actually explained getting r by itself and how it works, but I don't think that's necessary general knowledge that you need at this point. So that's helpful. That gets you, I think, through the bottom part of page 3, and I'll move on to page 4.